Hi, year 13. So here's your retrieval roulette for today. So pause, get answering. And here's the answers. So again, pause, get those marked and corrected, and then let's get started with today's work. So just a reminder where we finished off on Thursday there. The principle of moments, if you have something which is in equilibrium, if it's in rotational equilibrium, then that means that the anti-clockwise moments are equal to the clockwise moments, and we can use that fact to figure out unknown forces. However, if you're told something is in equilibrium, you need to remember that, but you also need to remember that there's going to be no resultant force acting at all. So we could use the fact that, for example, all the forces acting up must be equal to all the forces acting down. So I just wanted to remind you about those two things because we are going to be using those in the examples that we're looking at today. So if you turn over to page 117 for me, then we can get started on these examples. Right, I know this question is like tiny on the screen, but you have it in front of you as well. Okay, so this diagram here shows the forces acting on your forearm when you hold a weight with your arm horizontal. Your elbow joint acts as the pivot. Clockwise moments produced by the weight of your arm and the weight in your hand must be balanced by an anti-clockwise moment from your bicep muscle. Use the principle of moments to calculate the force exerted by your biceps, and they've called that FB. So here's our pivot here. This one is it's just the weight of the arm. That is creating a clockwise moment. The weight that the person's holding is creating a clockwise moment. And then this one here, see, because the force they've drawn on is acting up the way, then the distance, remember, that we're going to need is the horizontal distance from the pivot, which is the elbow, to the force. So it's this wee tiny distance here. And if we follow that, that's going anti-clockwise compared to the pivot. Okay. So same as that example we did yesterday, this one's not too complicated. So start off by saying I'm going to take moments about this pivot, and then anti-clockwise moments are equal to clockwise moments. So anti-clockwise is the force multiplied by the distance. The only one we have is this one, so that's for FB. And then clockwise, we've got both of these. So we'll have the moment, the force multiplied by the distance for this 20 newtons, plus we've got the moment of this 60 newtons one. So force multiplied by distance for the 61. Fill in your values. So FB is what we're looking for. The perpendicular distance to the pivot here is 0.04. 20. And the distance it is to the pivot is 0.16. And then for this one, 60. And the distance it is to the pivot is 0.32. So remember, they will be sneaky and they'll not give you the total distance a lot of the time. You might need to add or subtract distances to find out. So distance from this one to the pivot, 0.32. Just maths from there on in. So 0.04, oops, FB gives 22.4, this all gives you. So if we divide by 0.04, we get 560 newtons, which makes sense because that's way bigger than these ones, but it's such a short distance from the pivot, so it's going to have to be a really big force to give the same moment. Right, let's look at this next one then. So a diver weighing 650 newtons stands at the end of a uniform, so the weight's distributed evenly, 2 meter long diving board of weight 200 newtons. So quite often they will tell you that, but they'll not actually mark it on the diagram. They have in this one, so that helps us a fair bit. So there's the weight of the diving board, 200, and because it's uniform, that's 1 meter from either end. There's our diver, 650 newtons right at the end. What are the reaction forces at the supports A and B? So they've already labelled them if the board is balanced as shown in the diagram. Now sometimes people struggle to visualize what's going on here. So it's like this is like wedged in between these two. So this is pushing down on this and this is pushing up on this. Okay, and then whenever she stands here, I suppose it's really going to be like kind of bending like that a little bit. Okay, so I've forgotten what we'll have to find. The reaction forces. So we've got two unknowns in this one. So this is one that I have been going on about, where we can like decide where we want to take moments from. So we could either take moments about this point A or this point B. And the reason that they're the only 2 points that I would choose to take the moments from is that if I take moments about this point A here, then because this reaction is 0 meters from that, it's not going to create a moment, so it's not going to appear in our anti-clockwise moments equals clockwise moments equation. Similarly, if I take moments about this point B, then we can discount this R2 because it's not going to be creating a moment, because it's acting literally through the pivot. So I took moments about B. So let's have a little look at this. If this is my pivot here, this one here is making this turn anti-clockwise. This is not going to be creating a moment because, as I say, the distance is 0. This is clockwise, and this one here also clockwise. So labeling those on the diagram can help you to fill in like your next line of your working out. So we only have one anti-clockwise, so we'll have the force multiplied by the distance for that wee R1, is that? Yeah. And then for our clockwise, we're going to have the moment, force times distance, for the 200, plus the moment for this one, so force times distance for the 650. Fill in our values. R1 is this force. Distance to the pivot is 0.75. This one, 200. Now we have to figure out this distance. See the way that's 1 meter and that one's 0.75? Well, this wee distance here must be 0.25. Plus force times distance for this one, 650. Distance to the pivot is going to be this 1 meter plus this 0.25, so 1.25. And then I'll just do the rest of the maths here to solve for R1. There we go. So that's what we've got for R1. Now, to find R2, one of the things that we could do would be to take moments about part A, because that's going to eliminate R1, and we can do this whole process again, and that's going to be our only unknown. But there's a wee quicker way that we can do it. We can use the fact that we know if something's in equilibrium, then the forces are balanced, so all the upwards forces are equal to all the downward forces. So that's the way I would choose to do it, just because it's a little bit quicker once we're left with only one unknown there. So if I'm looking at the forces vertically, and again, show the examiner you know what you're at, so I'm going to write in equilibrium, or sometimes I just write like up equals down. So if we look back up at our diagram, the forces that we have up the way is just R2, and then down the way R1 plus 200 plus 650. So R2 is R1, which is 1150, plus 200 plus 650. So that gets us 2000 newtons. So there's our two forces found. Now, I do also want you to add in a wee extra note over here about the other way that we could have done that. So add that wee bit in there for me, please. So we could have taken moments about A to get R2. Right, over on to 118 then. So this one here, not too bad. The one at the bottom of the page is a good one. So a stage lighting batten consists of a uniform beam AB, which is here, 24 meters long, which weighs 600 newtons. Now I see if you have a quick look over here, you can see they have not marked on that 600 newtons. So because this is so tiny, I always redraw. I'll either just mark things onto the diagram that we've been given, or I'll redraw if it's too small. So for this one, we need to redraw this diagram here. So I'm going to draw it a bit bigger than it is. So there's end A and end B. 24 meters long. I will mark the 24 meters in a little bit. And it weighs 600 newtons. So that 600 newtons is smack bang in the middle. Okay, I'm going to mark that distance in a wee bit as well. Bear with me. The batten is suspended by two vertical cables C and D, so they're here. So we're going to have a force up the way here at C and a force up the way here at D. It tells us that each cable, or the tension in each cable, is 430, so I'm going to mark that one. Okay, and then it tells us that the batten supports two spotlights S1 and S2, each are 70 newtons. So I've got S1 just from up here, 70 newtons, and S2 is at the other end, so that's here, and it's also 70 newtons. Floodlight F of weight 120, so again I'm looking back up here to see that where that is. It's 16 meters, so it's going to be to the right of this, isn't it? Yeah. So F, and it told us that that was 120 newtons. So the arrangement and distances are shown here. Then it's asked how far is cable C, so this one, from end A. I'm going to mark on all the distances that we know now. So let me see. This here distance is what we're being asked for, so we don't actually know that. The next one along is to the 600 newtons. Now this was the batten's weight, and we were told that this was 24 meters long, and we were also told it was uniform, so we know the weight is going to be acting at 12 meters from one end. F, it told us, was oh sorry, it was marked on up here, 16 meters. And then the next one along here is going to be this, the one until this point D. Now see if we look back up here, it told us that this wee length here was 2 meters, which means that from this end to here must be 22 meters, and then to the very end is obviously the 24. Now you might think that's overkill, but to find this I'm going to end up taking moments about this point here, and now it means that I have all my distances from this point, so it will help with the working out. So taking moments about A, we know anti-clockwise equals clockwise. So let's have a wee look at this. So S1 is not going to create a moment because the distance is 0. Anti-clockwise we've got C and D, and then clockwise we've got the 600, the 120 and the 70. So I'm going to fill out my next line there. Okay, so for my anti-clockwise I've got the force times the distance, the moment for C, plus the moment for D, because there are two anti-clockwise ones. And then for clockwise I've got the moment for the 600, plus the moment for this 120, plus the moment for the 70. So I'm just going to fill in my values there. So C was 430. Distance to the pivot is what we're being asked to find, plus D, 430. Distance it is to the pivot is 22. 600. And the distance it is to the pivot is 12. Next one is our 120. Distance it is to the pivot is 16. And our 70, and it's at the very end, so the distance it is to the pivot is 24. So I'm just going to tidy this all up. So 430D plus 9460 equals, these all add up to 10800. So this wee distance here is 3.12 meters. Check, does that make sense? Yeah, it's smaller than all of these. Quite close, yeah, makes sense. Right, this last example is a good one. So a wheel of radius 0.5 meters, so they have marked that on our diagram there. Rests on a level road at point C, so there it is resting there, and makes contact with the edge E, so they've called that wee point there E, of a curb of height 0.2 meters, and that's marked on as well. A horizontal force of 240 newtons, so this was like the driving force, is applied through the axle of the wheel at X, so that means it's right in the centre. That size of force is required just to move the wheel over the curb. Find the weight of the wheel. So in this one they haven't marked on all the forces that are acting, so let's mark them on. We're obviously going to have the weight of the wheel, which is acting down there, and that's what we have to find. We're also going to have a reaction force, and it's going to act from here through that centre point there. In the end we can ignore it, but I'll talk about that in a little second. Other distances we will get in a wee second, but that's all our forces. So we have to find this unknown here. This is the point that we're going to end up taking moments about, and because this here reaction force acts through that point, it doesn't create a moment, which means that we can eliminate it from our calculation. And that is the key to a lot of these questions, sort of being sneaky about it and getting rid of something that you do. That means you've one less unknown. So we don't actually have the perpendicular distance from this 240 to here, or from this weight to here, so we're going to have to figure those out. Now this one is easy enough, because see the way from here to here is 0.5 and here to here is 0.2. Well, that means the perpendicular distance from this 240 to this point E is going to be 0.3 meters. We also need to get this wee distance here. It's a bit harder to figure out. I'm going to call it X for now, and then we'll work it out over here. So to get the perpendicular distance from E to the weight, I'm just going to redraw. Here's my point X, here's my point E, and we know that this length here is going to be the radius of the wheel, so it's going to be 0.5, and then we're going to have the weight acting down there, so it's this distance here that we're going to need. But if we look up here, this wee distance here is 0.3, so that means we can use Pythagoras to figure out this wee unknown here. That's a wee Pythagorean triple, but we'll do our working out properly. So 0.3 squared plus x squared is 0.5 squared. If we solve that, we get 0.4 for x. So this perpendicular distance between the weight and the edge of the curve is 0.4 meters. Now, next little note is just to make a wee note about taking moments about E, because then that means we can eliminate the normal reaction. So if we take moments about E, it means we don't need to worry about R. So taking moments about E. Anti-clockwise equals clockwise. So let's look back up at our diagram. If I'm taking moments about here, this is anti-clockwise, and then the 240 is clockwise. So for anti-clockwise, we've got force times distance for the weight. Clockwise, force times distance for that 240. Fill in our values. So the force we're looking for is the weight. Perpendicular distance to the pivot is that distance x, which is the 0.4. And then here our force is 240, and perpendicular distance from it to the pivot is the 0.3. That gets us 180 newtons. Okay, so that's a wee stinky one there. So I think that is all I'm going to be asking you to do today, and then next lesson it'll be some of those questions that are in our notes. We're not going to do them all. I'll pick out some for you to do. Okay, so that's us for today. Bye.